Hello, welcome to breadboarding. If you've seen the introduction video, you'll know that you can use solderless breadboards like this one to build and prototype and experiment with microprocessor-based circuits. And in fact, that doing this, you'll learn a lot more about how the hardware works than you would if you were building systems on printed circuit boards or using solder systems. What I'm going to be showing you in this video is the introduction to the design of the Nanocomp 6809 computer, as appeared in 1981 Wireless World. To start with, you might wonder, well, if I want to learn about computers, then why should I build a microprocessor on breadboards? Well, one of the problems with modern computers is they've got so fantastically sophisticated and complicated that it becomes very difficult to understand at the hardware level what's actually going on. So, for example, if you wanted to learn programming, you're probably better off to start looking at something like a Raspberry Pi, for example, where it doesn't really matter what you do with it. You can re-flash the SD card should you make a mistake. Now, what I'm going to do now is to go through some of the different types of processors and things, and just to show you how much simpler the original 8-bit micros from 40 years ago are, and how you'll be able to understand what's going on much better than you will with the more recent designs. So if you want to start learning about computers and programming, then probably the best place to start is with the Raspberry Pi. In fact, the Raspberry Pi 400 is probably an excellent way to start, because these you can get hold of. Some of the more basic boards are difficult to come by at the moment due to component shortages, but you can see that apart from a mouse and a power supply, it's about all you'd need to plug it into a monitor. Some of the other Raspberry Pis you might consider using if you can get hold of them. This is a very old Model B. You can see here that the chips are incredibly small. The problem with these types of boards and things is the technology in these things is incredible, but trying to work out how everything works is really quite difficult, and an awful lot of the firmware that's used to initialize these computers is all proprietary from Broadcom. Now, probably one of the simplest chips around at the moment is an Arduino, which uses an AtMega328. So this Arduino Pro Mini that I have here has got an 8-bit processor, the Atmel 328P, I think, and this particular board includes 32K of flash RAM, a couple of K of RAM, and includes Bootstrap on there that loads everything up from the serial port, so the programs get automatically loaded from here. Now, you might think this costing a couple of pounds would be fairly straightforward and simple to learn, but in fact, when you find out the data sheet for this particular chip runs to many hundreds of pages. So just this sort of 8-bit chip with 32K of memory and serial ports and other I/O ports on here runs to many pages. In fact, if we go to the end here, we've got something like 290 odd pages. So this is for a very simple 8-bit microcontroller. Runs to hundreds of pages. By comparison, the 6809 data sheet that we'll be looking at in a bit more detail, this is quite an extensive data sheet, but this only runs to about 35 pages, and some of the latter pages are all to do with the physical pin layouts and things. So learning the older 8-bit microprocessors is a lot easier to understand how the hardware works than it is with the more recent ones like the Arduinos and AtMega chips. On a similar vein, we actually look at this is a Motorola 6809, so it's in a 40-pin dual inline plastic packaging. By comparison, some other chips that I've got copies of from older PCs that I've pulled the chips out on. So if you look at the Pentium 100 in this particular example, so this is from around, I think, 1992, I think the Pentium 100 is from. This, you can see, has many hundreds of pins. I think it's about 296 pins theoretically here. So even this chip, which is probably only about 10 years older than the 6809, it's very difficult to use this with breadboards and prototype. You could only really use this with quite a complex multi-layer printed circuit board. So then moving on from the Pentium 100 there, towards the late 90s, the AMD K63 here, very similar. Not much has changed really. I think there's 321 pins here rather than 296, but still, way too many to work with. And then coming more up to date, this is an Intel Core 2 Duo from around 2005, and this no longer has pins, it just has pads underneath. And I think this one has about 775 connections. And if you look at the more recent Intel i5, i9s, the most recent versions of those now have 1700 pads. So what you can begin to understand is that to try and understand how the hardware on any processor after about 1980 works is really quite difficult, because they're so complicated and there are so many layers involved in them. So what we're going to be able to do with the Nanocomp is understand how the hardware works from a very, very basic level, and getting an operating system working and the keypad and all this sort of stuff. So I think you can learn a lot more about computers and how they fundamentally work with breadboards and these 8-bit microprocessors than you could with any of the more recent computers using Intel or AMD chip. So what we're going to do now is to have a look at the Nanocomp 6809. First version of this appeared in Wireless World magazine in January 1981. The first version of the Nanocomp was based on the Motorola 6802 microprocessor. This was the predecessor to the 6809. This was almost like a microcontroller because it included about 128 bytes of RAM at the bottom of the address space, and this was followed up in July 1981 by a new version using the 6809. So what I'm going to do is to just look at the versions of these online. So the Wireless World magazine is available as a PDF download on the internet. So this was the first one, and you can sort of see that quite yellow and not that clear to read. So this was the first version, and then we have the 6809 version. And what I've done here is I've actually got the physical copies of the original magazine that I cut out of the magazine before I threw it away. And what I've done here is scan using a black and white scanner, and then printed out and made it a little bit easier and clearer to see. So this is the original Nanocomp, so I'll get rid of the original details here. So you can see the Nanocomp design included the keypad and the 7-segment display, and included the input-output connections from the peripheral interface adapter were also available for interfacing on the front here. I won't go through the details here. I've got a slightly easier to see diagram. You can see here this is the original 6802 version of the diagram. We'll be looking in more detail at the 6809 version. It's very similar, just a few minor differences around the way how some of the clock signals and things work. But you really need to read through both the articles to get the full background to what's going on with the Nanocomp. Includes sort of power supply, and the printed circuit board layout is sometimes, I know, is useful to just verify some of the schematic key layouts and things. And then this page here is particularly, we'll come back to, in the way how the 7-segment displays are normally referred to as A, B, C, D, E, F, and G, the way how I think these two here are mapped between E and F, I think is transposed between the Nanocomp design and between the standard data sheets and things. So this was the original January 6802 version, and then we've also got the July version. So again, the original and slightly cleaned up version. I will make the PDF scans of these available with all the code and the KiCad schematic designs for this when I upload these onto to GitHub at some point in time. So for the 6809 version, you can see the memory map here in that the ROM or the EPROM is in the top 4K. The reason why the RAM starts at 1000 hex rather than at 000 is because the 6802 had 128 bytes of RAM in the bottom, starting at 000. So in order to allow the same monitor ROM or similar monitor ROM to use between the two, I don't think they changed that. So there are some minor circuit modifications. I will go through an A3 version of this diagram in a few minutes, rather than going through this smaller one. A lot of this article was about the specifics of the 6809, particularly the design and architecture of it, because there wasn't much information available about the 6809 at this point in time. So quite a bit of it was all about the various instructions and addressing modes. The nice thing about the 6809 is it had a fairly small number of unique instructions, for about 52, 54 unique instructions, but there were loads and loads of addressing modes. So there were more than 1,000 combinations of instructions, but this was just the 50 or so basic instructions expanded by the addressing modes. And you can sort of see from this table that the way how the various second byte included all of the flags and indicators to determine the type of addressing that you were doing. The other thing about this particular design is it included a cassette interface, so you could save and restore programs to audio cassette, as was common with computers at the time. And in fact, the printed circuit board layout there, I think we'll see in one of the examples I've got of the board I built 40 odd years ago, uses a very similar design. The other thing I should say here is that the PCBs and the ROM were available pre-built, and I still have a copy of the ROM, which I think was bought from Technomatic. This is the ROM that I pulled off the board. We just zoom in, see if we can see it a little better. So this is the original, I think it's a TMS 2516 2 kilobyte ROM. This still works, and what I'll be showing in later videos is using an EPROM programmer to read this and to burn this into some more up-to-date ROMs so that I don't fry this one. So what I'm going to do now is to go through the block diagram that I've put together here, so it'll be a little clearer to see than the block diagrams in the original Wireless World article. So the microprocessor is the Motorola MC6809. Now, this being an 8-bit microprocessor and a hybrid sort of 16-bit microprocessor, some of the internal instructions were 16-bit, but it talked to the outside world over an 8-bit data bus. So these were normally known as D0 to D7, so this was both input and output, the data bus. We then have control signals such as a reset line, the E clock line, which is used to determine when the microprocessor reads and writes to memory, the read-write signal that determines the direction of the data bus, and then some interrupts. So non-maskable interrupt, I think, is used by the abort key to abandon any current running program and to go back to the monitor. And the IRQ interrupt can be used for things like serial ports and peripheral interface adapters to alert the processor to go and do something when a character arrives, for example. The address bus on the 6809 is 64 kilobytes or 16 bits, normally known as A0 to A15. In this particular design, though, the top A15 address line is not used, so it means that the only the bottom 32 kilobytes of address space is used on the Nanocomp design. And so this means if anything tried to talk to the higher levels, then it just maps it back to the lower 32K. So then the microprocessor is driven by a 4 megahertz crystal clock, and this is then internally divided down to 1 megahertz. So the E signal, which is used externally as a clock, is at 1 megahertz. It's due to the way how the clock signals are in quadrature, out of phase, as you'll see when I look at the logic probe looking at the 6809. The reset logic then makes sure that the microprocessor doesn't come out of reset state when the power switched on until the clock is stable and until the power supply is stable. So I think the reset is about 100 millisecond delay before it comes on. And then one of the other key things that we'll be looking at is the address decoder. What this does is takes the 3 most significant address lines. So this divides the 32K of address space that we're using into 4K blocks. And what this address decoder does is takes those 3 address lines and takes the clock signal E and then generates a number of chip enable signals. Normally chip enable signals are active when they're low, so you'll normally see a bar or a slash associated with these. So in this particular case, the read-only memory, or the ROM, is driven by the Y7 signal. So that means that when memory address of 7000 hex will be where the ROM starts. RAM memory starts at 1000 hexadecimal, and you can see here that it has two-way interactions with the data bus, whereas the read-only memory will only be sending data to the data bus. And then the peripheral interface adapter, or the PIA, is what's used to handle the 2 ports known as port A and port B, and this controls the 7-segment display in the keypad. The way how this works is we have an LED 7-segment display with 6 digits. The port B, line 0 to 3, drive a decimal decoder, which gives you lines 1 to 10 or 0 to 9, depending on how you want to look at it. And those outputs are used to drive the common cathode in the LED display. And what happens is the monitor running in the ROM will very rapidly refresh each of the 7-segment displays in a loop, so that the display looks like it's static, but in fact it's being refreshed very rapidly by the monitor when it's waiting for keyboard. And the segments which are displayed is controlled by the port A address line, the port A lines here, and those go through Darlington driver transistors, and we'll talk about that in a little more detail when we go into the circuit diagram. But the 7-segment display is controlled by which display is being used by the decoder, and then which of the 7 segments A to G are lit, dependent on the values going out to the Darlington transistor drivers here. And then finally we have the keypad. Some of the keys, so the reset drives the reset line, the abort button drives the non-maskable interrupt line, but the keypad is using the row 0 to 3 and then listening on port A to see any key pressed will ground the line, the port A line, to 0 volts, and so the monitor here will look for keys being pressed, and then when the key's released, then it will send the keystroke back to the monitor for processing. So that's the block diagram. It's a pretty simple circuit. There's only about 6 or 7 chips used in this design. So before we look at the schematic diagram, I was just going to show some of the boards I originally found up in the attic. So this is the original keypad board that I built in 1981. You can see here that I've managed to lose the keycaps, not quite sure where they've gone. But we have the 7-segment display here, the keypad. This area here is the cassette interface. I've pulled all the chips. I remember at the time I couldn't get the chip with the Darlington transistors, so I just used independent transistors there. And if we look on the back, you can see here that there's a combination here where there's the printed circuit board layout from the cassette interface from the magazine, and there's also use of the wiring pen here. So this is the Roadrunner wiring pen that I showed in my introduction video, and this made it a lot easier to wrap the wire around the various pins, do your layout, and then solder them, and produce quite a reliable design here. So that was the KiCad, and originally I was already building 6809 based design before the Nanocomp design came along. So this is the original processor board, and you can see here that there are a number of buffer chips that I designed for this. The data line buffers and the address line buffers. But since the Nanocomp was only driving about 4 chips, there was only about 4 chips being driven by the processor, but it didn't really need the buffers for the basic design. So you can see here they just had some wires short-circuited the chip signals there. And you can see on the back there that this printed circuit board was built using transfers and then etching it using iron chloride. This is then the board that was built, that I built once the Nanocomp design had been published. So I evolved the design to do this, and you can see here it's using the wiring combs, and the Roadrunner wiring pen is also used here. It's a bit of a mixture between using a printed circuit board for the various connectors and power rails and things, and just using the wiring comb for hooking up the individual pins and things. So this was working. I did try and get this running when I first found it, but there were the connections and things and the chips were a bit corroded, and so I didn't get any further on that. So I thought, well, let's rebuild it on a breadboard and see if we can get it to work, and which is what we're going to be looking at in the upcoming videos. So what we have down here at the bottom here, this is the microprocessor, the 6809. You can see we have the data lines, the address lines, and there's the clock down here and various control signals and things around here. There's a read-only memory here. In this design there were multiple chips supported. The one that was used in my example was the 2516, and then we have the 2 RAM chips here. This was 1 kilobyte of RAM. The 2114 RAM chip only included 4 bits, so you needed 2 RAM chips to give you 8 bits for making a proper byte. This will be replaced in the new design with a larger static RAM chip that will just be using 4K of its address space. Then we have the address decoder over here, and feeding into here we can see there's the top 3 address lines which are in use on the Nanocomp, remembering that A15 is not used in Nanocomps, are only used in the bottom 32K of address space. And then this is combined with the E clock signal from down in the microprocessor here, and that controls the chip select lines on Y1, Y4 and Y7. So then we have the PIA, or the peripheral interface adapter. This provides port A here and port B, which are used to drive the KiCad and the 7-segment display. Key thing to notice here is that the PIA has 4 registers, 2 for the data input and output and 2 control registers, and the A0 and A1 lines here are actually mapped the wrong way around, or the different way around. So A1 goes to 0 and A0 goes to 1, and it's important that these are wired up this way because the monitor ROM, as it stands, expects the address lines to be mapped in this way, and if you don't do that then it won't work. So you can see here that the port B here, that the 4 lines there provide values from 0 to 9 or 1 to 10 depending on how you like to think about it, and those are decoded by this decoder chip over here. And all these outputs, when an output's selected, it will go to ground, to 0 volts. And because all of these, as we said before, are common cathode, then when this line goes to 0 volts, all of the 7-segment pins are held at 5 volts. And so by default, when this line goes 0, all the segments will be illuminated. And in fact, what happens is the values coming out of port A, that if there's a 5 volt or 1 value on the port here, it results in the transistor being enabled, and in fact it will ground that segment value, and so it will turn it off. So in fact, in this particular case, a 1 will turn off a segment and a 0 will leave it on. And what we'll see is when we go into the system monitor ROM, when we look at the assembly language there, we'll see that before a 7-segment value is sent out to this port, it is complemented, or it's inverted. So a 1 becomes a 0 becomes a 1, and that in order to do the display here, then it will be automatically inverted. And what the monitor ROM here does is ensures that each display, each segment, each display is refreshed for a few milliseconds, and then in between each of the displays being refreshed, it will also be scanning for keys to be input as well. Right, so that's the schematic. What we're going to do next is to look at the schematic in KiCad, which is an open source free computer aided design package which allows you to do schematic diagrams and can also be used for building PCBs. But for this purpose, what we're going to be doing is looking at it for building out a schematic diagram that helps us to build the breadboard layout. So this is the KiCad schematic that I've produced for the original Nanocomp design. So if we look at the Nanocomp, so you can see here we've got the processor, we've got the ROM, we've got the RAM, we've got the address decoder, we've got the PIA, we've got the Darlington transistor driver, we've got the decoder, BCD decoder here, and we've got the 6 7-segment displays. So this is using KiCad. KiCad is a sort of free open source computer aided design package which includes schematic and printed circuit board designs. I'm only going to be using the schematic editor in this particular case. Now, there are some other tools that I've looked at for doing circuit diagrams for breadboards. There's an interesting one called Fritzling, which I'll show a little bit later, which has specific layouts for breadboards and also for stripboard or veroboard. And I've used this for certain things like the keypad, for example, where using the PCB designer is a bit cumbersome. It is theoretically possible to do layouts using the PCB designer, but it's not really very easy to use, or I didn't find it very easy to use. KiCad 6 has been just released in the last sort of 6 months or so and is a big improvement. The one thing I do find is that trying to use this on a laptop with just a touchpad is rather cumbersome, and you certainly need to use this with a 3-button mouse, really, with the middle wheel. So let's just go through the diagrams here and I'll explain a few things that I've done. This is a little different from a normal schematic. A normal schematic, you try and make it as clear as possible to understand the schematic. What I've done with these is try and lay it out in the way that I'm likely to lay it out on the breadboard. And in particular, when we look at the chips here, you'll see that there's a default layout in KiCad for chips. We'll quite often group all the similar pins together and we'll move them around on different sides of the chip. Now that's great for making simpler schematics, but the problem is when you're trying to work out how to lay out the wires and the orientation of the various chips and things, it does make it more difficult. So what in fact I've done here is gone into the symbol editor and created my own breadboarding library where the standard chips have been taken into the editor here, and then I have changed the pins such that rather than being organized from a logical point of view in a schematic, I've reorganized the pins so they come out in the physical order. And this is all saved in one breadboarding library again, which I'll put up onto GitHub once I've finished all the diagrams here. So these are the pinouts are very similar to the standard pinouts that come with KiCad. The only difference is I've relabeled them so that the pin numbers come out on the right way. And what you can see, normally you would always include pin 1 on the top on a circuit diagram generally. In this particular case, I've put pin 1 down the bottom here because it makes the layout a bit easier. So when we come to stick things in the breadboard, then sometimes it makes sense to change the orientation of the chips to make the layout neater. So this is the reason why I found that using KiCad, and you can see here as well, rather than using the more traditional, having the VCC and the ground at the top and the bottom of the chips, by including the sort of red and black rails along the side, it more accurately reflects the way how you would lay things out on a breadboard. So what we've got here then is our basic processor, and we go backwards and forwards between the schematic. We can see that here the A15 line is not in use. So in KiCad, generally, if there's a pin not used, it's a good idea to mark it as not in use, and then the inspection rules checker will not advise you that you haven't connected that particular pin. So if we go back to the schematic, you can see down the bottom here, I just get a pen. So we can see down the bottom here that we've got the positive supply rail VCC. There's number control pins, so the halt, the memory ready, the DMA bus request are not in use, so they're just tied to 5 volts. You can also see decoupling capacitors also here. The clock circuit here is a 4 megahertz crystal, and then with 2 small value capacitors. So we can see, we switch back to the main screen here. So you can see here we've got the memory ready, the DMA bus request signals here, and we've also got the crystal signals here. So the only problem we have with the crystal signals is because they're so close together, the crystal's actually a couple of tenths of an inch wide, and so you tend to need to put it slightly above the chip. You'll see this when we do the layout, but what this helps to do is to work out how to lay things out on the board but still maintaining a proper schematic. And then we can see the data bus here, and generally within KiCad we would label the buses with this type of syntax, and what that will do is it makes sure that all the appropriate bus signals are connected, and we can see here all the address lines here connected to the address bus. And again, we've only got A0 to A14 because A15 is not used here. Now, what we're going to do to start with on the breadboard, I'm just going to build this part of the circuit here. So we're going to do the clock, we're going to do a basic reset circuit, although we will put a reset button on the breadboard to start with before we build the keypad. And then after that, what we're going to do is to add the address decoder, and this is going to provide us with the various Y1, Y4, Y7 signals. The Y1 is for the RAM, Y4 for the PIA, peripheral interface adapter, and Y7 for the ROM. And then once we're going to build this initial clock and reset circuitry, what we're going to do is, there's quite a neat trick that I've seen on a number of other sites, which I'll try and find the references for, that if there is an instruction in the 6809 instruction set called no operation, or no-op, and the no-op instruction basically says to the processor do nothing. It just basically uses a couple of clock cycles and then goes on to the next instruction. Right, so here I have, we're on page 29 of the data sheet, and we can see here that the no operation code here is actually hexadecimal 12. So if we put the hexadecimal 12 on the data lines, then what that will tell the processor to do is do nothing and go to the next instruction. And the next instruction will also be no operation. Now what that has the effect of doing is just makes the processor count through all the address lines. And so what will happen when we look back in the, what will happen is, because every time the processor tries to get something from the data bus, it gets the value 1, 2, no operation. All it will do is end up counting all the way up through the address lines, and provides quite a nice way of testing that the processor's working properly, because all you have to do is then look at these address lines, see whether or not they are ascending in order, see if any address lines have not got any values on them. It allows you to see whether or not the processor's working in quite an easy way. So that's the first thing we're going to do. In the next video, we're going to be using the breadboard to set up the processor, the clock circuit and the reset circuit, and see whether the address lines increment in the way that we've been talking about during this current video. If you don't want to miss out, please hit subscribe. Thanks for watching.